Hi everyone, thanks for joining us today. My name is Stephanie McLean and I am the State Soil Health Specialist for the Natural Resources Conservation Service here in Indiana. Today we are going to talk about the Infield Soil Health Assessment. All information pertaining to the Cropland Infield Soil Health Assessment can be found in Soil Health Tech Note 450-06. This Tech Note was recently released via e-directives on December 10, 2020, and you can find all information pertaining to it there. Here is what the Cropland Infield Soil Health Assessment Worksheet looks like. There's a lot of details on this worksheet that we will be going into throughout the day. Another item that can be found in the Infield Soil Health Assessment Tech Note is this management history sheet. These are a series of questions that you can use when communicating with your farmer to help better understand what their management practices are. This is by no means a required document that needs to be completed, but these are just questions that kind of help you figure out what's going on out there. Also, for our beginning conservation planners, this can help you build the questions that you use, and they are key to understanding what you see in the field. Before we delve into the assessments, let's take a step back and think about what these assessments are meant to look at, and that's soil function. We want to look at, through these assessments, whether or not our soil is able to infiltrate, store, and filter water, whether our soil can cycle nutrients, breaking down residues and then releasing those nutrients into the soil, and then those nutrients are then being re-released back into our plants, that cycling process. We're looking to see if our soils are a physical platform on which to farm, looking for physical stability. And then also we're looking to see if our soil is a habitat for soil life, which ultimately can be one of the most important functions that we're looking at, right? Because when we have a healthy soil, we have a living, breathing ecosystem in which all these organisms are there thriving, building a soil habitat, and it benefits plants, animals, and us. And then these organisms that are creating that habitat in the soil, they are responsible for 90% of the soil function that we're talking about here today. When this all is working together and we have a high soil function, we start to see resiliency in our cropping systems. And by resiliency, I mean that our soil ecosystems are able to bounce back after, say, a disturbance event or other things like that that can cause damage in the system. Resiliency to extreme weather events, whether that be droughts or floods. These ecosystems tend to hold themselves together better and can recover more quickly from those types of things. And so that's really what we're looking at when we think about soil function. So what are we talking about when we think about these assessments? Are we thinking about soil health, or are we thinking about soil function? And really we're thinking about both, because you have to have health to have function. And health is the overarching process and things that we're looking at, right, with those key principles that we talk about with soil health. But soil function really delves into the actual assessments that we're looking at, delves into the actual functions of the soil. And so we really need to have both of them for this system to be working properly. To always think about function as having function. So often people come and talk to us when they are missing function, when they're having these problems on the landscape. And that's when we start to piece together that we've had a loss of function. So when our soils aren't able to infiltrate or store water or filter that water, that's a loss of function. When our residues no longer are the resource of nutrients in our cropping systems, they tend to, when we see them building up and not breaking down or washing away when those fields are flooding, that's an example of a loss of function. When we don't have physical stability in our fields, a great example of this, when you know when a field doesn't have physical stability, is when you walk in it and your shoes come out 2 or 3 sizes larger than when you went into that field, because again, those soils aren't staying in the field or sticking to themselves. They're actually that those broken down muddy soil particles are just adhering to your shoes and then binding onto that, and you're carrying that mud out of the field. Again, great evidence of a lack of physical stability. And then lastly, when we are losing that habitat for soil life, when we have that soil that's crusting at the surface, and then we have that ponding or flooded situation, those soils are staying saturated for longer than normal, and we're losing that principal oxygen exchange or that gas exchange into that soil, because so many of our soil organisms are aerobic, and so they need to have that air exchange. And if our soils stay saturated too long, or after they're flooded they crust over, so again we have a difficulty in exchanging air in that system, we're losing that habitat, we're losing that biology in that system. And when we see all of these things start to stack on top of each other, we start to see no resiliency in our cropping system, right? And when we look at that, what we think about is the fact that these soils are extremely impacted by weather events, by extreme weather events, droughts and floods and other things like that. That they are impacted by this and are unable to function, or when things do happen, a disturbance or something that can set these systems back, they don't recover as quickly. And so that is evidence of a loss of function in these systems. Here's the list of the assessments that we're going to go over today. There are 11 of them on this list. I like to refer to them as soil health diagnostics. And the reason why I like to use that term is because it's a term that is used regularly in agriculture with crop consulting and scouting in fields and things like that. Diagnostics in the world of crop consulting are sound, replicatable things that you can do in the field to look for either problems or other things that are happening out there. And once you go through this process of diagnosing what's happening, that crop consultant can then give the farmer information and recommendations as how to move forward. And that farmer can then make a sound, educated decision based on the diagnostics and the recommendations that they received. Examples are like looking at, scouting for weeds or scouting for aphids. It's all about the numbers that are out there and the economic thresholds, or if we're looking at nutrient deficiencies in the plant, looking at the coloration of the leaves and where the colors are, where the deficient colors are, if it's in the vein or if it's interveinal or if it's on the leaf edges. All of these are diagnostics that the crop consultant can use to give the farmer information. And the farmer can take that information and make a sound, educated decision as how to proceed with management. And that's what we want to do here with these assessments. We want to be able to go out into the field and diagnose what's going on. By using these assessments, we're making these diagnostics, and then we can give that information to the farmer, and that farmer then can make a sound, educated decision on how to move forward with their management to improve the things that we and they are seeing in the field. So here's a look at the soil health assessment worksheet again. I just want to point out a few things here. The first thing is the indicator timing and use. So this kind of highlights when these assessments can be done, or let's just say the best time or the optimum time for when the assessments can be done. The next thing that we're going to look at here is the list of the soil health resource concerns. And each one of these resource concerns has a 3-digit code associated with it. And you'll notice those codes corresponding behind each of the assessments. So residue breakdown as an assessment feeds into soil organic matter depletion and soil organism habitat loss or degradation. Whereas water stable aggregates feeds into, that assessment feeds into all 4 of those soil health resource concerns. Lastly, the column on the right is a very simple yes or no response, just asking if it meets assessment criteria. So that site that you are at, we have a description of what the assessment criteria is, and then you just respond basically whether or not that site meets that assessment criteria. On the back side of the Infield Soil Health Assessment Worksheet is our decision trees. Each one of the soil health resource concerns has a decision tree. And in that decision tree it lists the assessments that feed into it. So for compaction we have 5 of the assessments that feed into that evaluation. Soil organism habitat loss or degradation, soil organic matter depletion, and aggregate instability all have 8 assessments that feed into making the determination as to whether or not that resource concern is present. So then we look at that, and the next part of this decision tree is a box where it asks a question. For example, do 2 or more of the indicators not meet assessment criteria? Or here for organic matter depletion, do 3 or more of the indicators not meet assessment criteria? So again, that goes back into how many, for organic matter depletion, how many did you say no to on the other side of this page that they didn't meet assessment criteria? And if there was 3 that didn't meet, then you would say yes, soil organic matter depletion is a resource concern. Here we have listed some of the tools that will be useful when going to the field. This is not an all-inclusive list, so if you have other tools that you utilize during your field visits, that's just fine. So if you take the list that we have here, you'll see I have a bucket at the top of the list, and what I like the bucket for is to take everything else on that list and I put it in that bucket, and I use that bucket to carry all of this out to the field. Then when I get to the field, I like to take that stuff out of the bucket and then use the bucket, I tip it over, and I use the bucket for setting things on to take photos of or for note taking. And it's also a very handy dandy chair when you need to have a seat out in the field. Other than that, you know, it's really important to have a shovel, a knife. The water there is for the sink strainers in the infiltration ring, so make sure you bring your own water to stay hydrated. We have a series of videos today that we're going to use for the infield soil health assessments. And we're going to start off with a video demonstrating soil cover and residue breakdown.
So 2 of our important soil health indicators have to do with surface cover, and of course surface cover is one of those, but then surface decomposition, surface cover breakdown is the other one. So here's a good site to discuss kind of some of those things. It's right after harvest. It's actually December. We've got corn stalks out here, and already we see that, you know, we've got probably 70 to 80% cover. But as we think about how much cover will we have during that critical erosion period, we have to look at some of these parts of the residue, the leaves. A lot of these are probably going to be broken down or gone by spring. And since we understand that in this particular farm there's some minimum tillage that goes on, we have to also consider what will happen after maybe one pass of tillage in the spring that's right before we plant. So we take a look at this, and we've already got some cover. We also can take note then of the residue breakdown too. So if we dig this back a little bit, we can look and find, and occasionally we find 2-year-old cover. And so here's a corn stalk that's 2 years old, that's still here, still intact. We don't find very many more. However, we have had tillage here, so we shouldn't expect to see a lot of 2-year-old cover when there's been some tillage involved. However, what we usually consider is overwinter decomposition. Will usually, a rough figure to use is about 20% decomposition. In other words, we should have about, if we're starting here with 80% cover, by spring we may be down after the small, the thin, the low carbon parts of the corn plant are gone. We may be down to as low as 60% just by overwinter decomposition by spring. So this is something to think about. Then you have to understand that farmer's tillage system and say, okay, if we're going to have one pass of tillage, what does that one pass of tillage maybe cause in the way of decomposition? And so that could easily be another 20%. So now we're down to 40% potentially, and of course that wouldn't meet our surface cover indicator. Since we have tillage going on, a lot of farmers we have to ask, why are you doing tillage? And if one of the reasons they're doing tillage is to process residue, then we have to assume that the biology is not processing that residue. So that also becomes an indicator that doesn't meet the criteria if we're having to do tillage to process the residue. Now, if they're doing tillage for complete completely other reasons, then that's part of your discussion with them. But if they're having to use tillage to process the residue, then we probably don't meet that natural decomposition criteria either.
One of the most important factors in promoting soil health is to keep the soil covered. Quite simply, soil cover is the percent of the soil surface that is covered by dead residues, mulches, and/or live plants. A lack of soil cover exposes that soil to erosion and detachment of the soil particles, and also reduces the food source for soil microbes. If we look at these photos here, the one on our right is a cornfield that's really close to harvest, but we have a cover crop growing in between those rows, and so in this picture here we probably already have over 75% residue cover. And with that addition of those corn residues and other things like that, depending on what's happening in the spring, we more than likely will meet the assessment criteria of 75% residue cover during that critical erosive period. If that field does go into a high disturbance tillage system, that will be pulling that number down significantly. In comparison, on the left, here we're looking at a recently planted field. We have a lot of residue out there, a lot of soil cover out there, but it's pulled into clumps and we have quite a bit of exposure. And so this would be an example of not meeting that assessment criteria. We don't have that 75% during that critical erosive period. Again, cover equals protection. This is the information that we really want to get across to our farmers and our landowners. The picture on the top right here is a picture of a corn crop that was planted into a chemically terminated crimson clover cover crop. So look at that amazing soil cover that we have there after planting. This would be, shortly after that critical erosive period. That soil may have been disturbed for planting. It's exposed to raindrop impact, but in this picture here in the top right, that soil is completely covered with residues. And in this situation, we're going to have the benefit of that legume cover crop breaking down or decomposing and adding nitrogen to that system for that corn crop. On the bottom right here we have a cornfield shortly after harvest, and we're seeing a lot of residues in there. And again, think about that protection from the temperature swings and from evaporation and raindrop impact. So we're protecting that soil life, and we're also protecting the function of infiltration by having that soil cover. So if we look at the assessment criteria, that's surface cover from plants, residues, or mulches, cover estimated at greater than 75%. So we really want to think about evaluating that management and operations to protect cover during the critical erosive period. So we have some pictures here just to kind of talk through again. Here on the upper left-hand side we have a cornfield. I went in between these rows. This was taken in early November, right before harvest. We have a cereal rye cover crop on the ground, so we have some residues there at this point in time. But if we think about that critical erosive period of next spring, we're going to add some residues onto that system, and if that field is planted with a no-till management system, we more than likely are going to keep that cover at over 75% or an estimated 75% during that critical erosive period. But if the system is going to have any type of disturbance at all after harvest or in the spring, we're going to be pulling that number down. Picture here in the middle, again, this is probably a prime example of when we're able to get out in the field and do some of these assessments, which is not necessarily the ideal time, but we got to get out there and do these things, and so we just got to go when we got to go. So this one is again a cornfield recently harvested, and we got some snow on it. So I would start by brushing that snow away and looking at that cover that's there, and then reaching out to that farmer and trying to figure out what are we going to see during that critical erosive period. But right there as it stands, we probably are at about 70 to 80% residue cover. And if we just go through normal decomposition over winter, like Barry was talking about in that video, we're likely not going to meet assessment criteria in the spring. Now, if you knew that there was a cover crop growing underneath that snow and that it was an overwintering cover crop, that would change that response, possibly depending on how that field is going to be managed in the spring. Here on the top right, we got a recently harvested soybean field. We got some cover crop growing in there. It was flown on. It's a winter cereal grain, like a cereal rye or a winter barley. So that's growing really nice. So does this meet assessment criteria? Maybe, right? This is kind of a hard one. Soybean residue, at almost any time during its life of being a residue on the soil surface, really struggles to meet that estimated 75% cover, because those residues break down so quickly and they just don't stick around for very long. But we do have that addition of that cover crop. So the question I want to come back here is to ask that farmer, how long is that cover crop going to grow? What is that spring management that you're going to put out there? If this cover crop's getting terminated, really early, so that that there's no residue sticking around in the spring when the corn is planted, this is not going to meet 75%. If those residues are those cover crops are planned to be grown as long as possible, if the farmer says that he or she is planting green and that residue or that cover crop is going to be terminated after planting or right at planting, you're going to have that 75% cover. And so again, thinking about soybeans on the bottom left, here's a prime example of what a typical soybean field would look like after harvest if it's just left and not having that addition of residues there. And that does not have 75% residue cover. In fact, it shows that a great example of a unequal distribution of residue across the field in general because of how that residue is getting distributed out the back end of that combine. So this is a great time to talk to that farmer about trying to get equal distribution of those residues so that you can have equal soil cover. Lastly, that picture in the lower middle, again, a soybean field, probably late June. We got quite a bit of residues out there, so we do have some soil cover, but it's been pulled all over the place and we have a lot of openings. And so just looking at that spot right there in the field, we're maybe at 50% residue cover, and so our soil cover, so that doesn't meet assessment criteria. So next, let's delve into residue breakdown. As it was described in that video, and what we're going to really want to think about is that natural shredding and decomposition of those residues. So this is an indicator, a relative indicator of biological activity. I kind of like to say that you don't want a corn stalk to see its third birthday. So we really want to think about those residues and how they are cycling through our system. Some of the things that we want to think about are how we want to handle that residue. We want to think about residue breakdown in high, medium, and low rates. So if we have a high rate of residue breakdown, when we pick up those residues in the field, those residue pieces are small, they're mixed into the surface, or there's minimal crop residues from more than one cropping season. When residue breakdown is medium, we have residue pieces that are close to the size left by the previous harvest, but crumble when handled, and crop residues are there from 1 to 2 cropping seasons. And then low, when we have low residue breakdown, the residue is in large pieces left after harvest. They can be handled without crumbling, and there's lots of residue from 2 or more cropping seasons. So if we look at this picture here, we're having some residue breakdown, but we're not having as much as we would like. I would call this medium. We got a lot of corn stalks that are left over that are the same size as when they were harvested. But when you pick them up, they do start to crumble as you hold them and crush them in your hands. Here's some other pictures that you want to think about, or these are some of the ultimate pictures of residue breakdown. That picture on the upper left, that hand holding that corn stalk with that fungi kind of having its fruiting body there, that mushroom growing in those residues. That's a great picture that you want to see. If you look at the scene behind that hand, you can tell we're in a cornfield. So this is that second year of corn, right? So this is our second year residue in this field, and it's about that size. If you would go through that entire field and look at the residues that are in there, the corn residue has all been pieced down to about that size. And this is in a no-till system, and so we've got good residue or high residue breakdown here. The other two pictures that we're looking at are from the most current harvest. So this field was harvested in early November, and we were out there about 3 weeks later, and these are this year's corn stalks and cobs. And so what we're seeing here is we're already seeing evidence of decomposition or of residue breakdown occurring on these most recent residues. You split that corn cob open, and that pith is starting to have that influx or that fungi or bacteria kind of moving into there and decomposing or breaking down that white material in there. Same thing goes for the corn stalk. We're actually starting to see those residues start to break down. They're losing color already. So those are good signs of high residue breakdown. Because we want our corn plant to carry us all the way through the growing season, but as soon as it's harvested, we don't want it to stick around too long. We want it to start breaking down as quickly as possible. As we look at assessment criteria for residue breakdown, keep in mind that we are really focusing on that natural decomposition of residue. So it's a biologically driven process. We want to see small pieces mixed in the surface and minimal residue remaining for more than one cropping season. So let's take a picture on this. Take a look at this picture on the upper left. This is springtime, and we're looking at some corn stalks that were harvested last fall. There's a little bit of weeds and stuff in there, but what do you think about residue breakdown here? Does it meet assessment criteria? No, this picture here does not meet assessment criteria. Those corn stalks, again, like I said, this is spring, and they were harvested last fall, and they're looking as yellow and fresh as the day that they were harvested, right? So we're not seeing any evidence of any bacteria or fungi on the edges of these harvested ends here. And again, those stalks are so yellow, they don't hardly even look like there's been any weathering to them at all. So these two pictures in the middle, they come from the same site, and if you look at the first one here on the left, there's a whole slew of different types of residues out there. We're seeing some soybean residues, we're seeing some small grain residue, we're definitely seeing some corn residue here. This was a harvested bean field this fall, and so that corn residue is over a year old here in this situation. And if you take a look at those residues, let's pick them up and see what they look like and how they handle. And you'll notice here that this corn stalk, we're still seeing that pith in the inside of that stalk, and it's not even discolored at all. And the same thing with that cob. Again, we're seeing that pith material on the inside of that corn cob, and it's not breaking down at all. So are we meeting assessment criteria here for residue decomposition or residue breakdown? No, we're not. Lastly, here's a picture on the right-hand side. This is in a cornfield, not harvested yet, but really close to harvest. And this was a cereal rye cover crop that the farmer planted into, and it was a pretty high biomass cover crop. And I actually pulled the residues away just to get a look at the soil surface. You might see a photo of this later on in the presentation, but if we put those residues back over that soil surface and then pick up those residues and crush them in our hands, it actually will crumble in your hands. So do we have assessment criteria here? Is residue breaking down? Yes it is. And if you think about it, in a cornfield, we got some cereal rye here. We're not seeing a lot of other residues in this system. And that cereal rye residue is doing what it's supposed to do. It's protected that crop and that field during the critical erosive period. It's protected that field during the growing season, during the heat of summer, reduced the evaporation, so we've kept that moisture in the field for the growing crop. And now we're getting into fall, and we're going to get an influx of more residues. And so these residues, they're weathered, they're old. You can see the spots on them. They're really grayed out. Again, they've done their job, and now they can finish decomposing into the soil, get pulled down and, get stored as organic matter, and let the next residues come in and start doing their job. Next, we're going to look at surface crusts. Surface crusts form when soils are basically overworked and left bare and exposed to the elements. That's when we start to see surface crusts occurring. They reduce emergence of our crops, they increase the risk of ponding and runoff, and they definitely decrease infiltration. So here we have some photos that were taken recently. The photo on the right is a well aggregated soil, and we've had that residue that was totally covering that soil surface, but it's been removed so we can look at that soil surface. And that's the way that you want to do this. You want to look at that soil surface and see what it looks like. That photo on the right, that's what you want to see. You want to see well aggregated soils all the way to the surface in comparison to the picture on the left. Here we have an example of a crust, and you notice how smooth it is on that surface, and it kind of washed out a little bit but in color, but when you go to pick that soil up, it comes up in big chunks, big crusty chunks right there, almost layered like chunks. And so that's an example of what a surface crust would look like. What's interesting to note is this photo on the left actually comes from a field that is in a very low disturbance system, typically a no-till system, and also uses cover crops. And so this is just to point out that anytime soils are left bare and exposed, degradation occurs and crusts are formed. And so this just really ties back into the discussion on soil cover and residue breakdown. Again, we want those soils covered, because when we don't have cover, we have degradation and we have crusts that form. And here's a crust up close and personal. When you get that crust picked off the ground, if you look at it really carefully, you can see that layering of the soil in that crust. And so, if you think about what happens, we have raindrop impact. Those particles of sand, silt, and clay are knocked loose, and of course the sand settles right away, but then our silt and our clay particles are left hanging in that water and that suspension. And what does water naturally want to do? It wants to infiltrate. Remember that soil function of infiltration. And so that soil wants that water to infiltrate. That water naturally through gravity wants to go into the soil. And so that water is trying to soak into the soil. But that water has these silt and clay particles in it. So as it's trying to soak in, those silt and clay particles are actually clogging up the pores that the water is infiltrating into. And eventually those pores are completely clogged up. And that's why we see that layering like that, and then the water has nowhere to go and it has to run off. And so in this picture here, that layering, we are seeing those multiple layerings there. This is an indicator that that soil has been rained on numerous times, and that crust has not allowed infiltration to occur, and it again just layers that silt and that clay right on top of each other. So when we think about assessment criteria for this, it talks about crusting on no more than an estimated 5% of the management unit. And when you really think about it, 5% isn't very much. So when we get out here to look for crusting, again, there's critical times or optimal times that we want to go look at it. And our tractor here indicates that we'd like to go look at this before the field is worked. But this picture here on the top left, this is when I could get out, right? I wasn't able to get out before the farmer planted that field. This was the only time that I could get my field visit finished, was after that field was planted. But let's think about those things that I talked about earlier on. Crusting occurs when soils are overworked and left bare. And if there's anything that soil is, it's overworked and left bare. We don't have any residues there, very small amount of residue. And it's definitely overworked. We're seeing, that those particles breaking down. We only have really small aggregates there, and the larger aggregates look like they're almost rock hard. So again, we have a pretty worked soil. So we can assume that if we have a rainfall event, typical rainfall event in this type of growing season, that we're going to see crusting occur on this bare soil. So I guess this does not meet assessment criteria. The picture in the middle, again, we're looking at a soybean field, probably late July or late June, early July. We have a bit of soil cover on there, but it's not evenly distributed across that field, right? It's pulled into clumps. It's been kind of disturbed during that planting process. And so if we just kind of look at that immediate area right in front of us and we visualize, you know, a floor tile or a pie chart and try to think about, you know, what does 5% look like on that ground in front of us, we would say that this one does not meet assessment criteria. There's well over 5% of that unit that it has crusting on it. And the same goes for the picture up in the on the top right. You know, looking down at that soil surface, looking at that crusting and seeing more than 5% of that soil surface that's crusted. Lastly, on the lower right here, we're looking at a cereal rye cover crop after planting. It was pushed down, you know, so it's really well matted to the soil surface in most areas. And if you were to walk out onto that field again, you would see a decent amount of soil cover, you know, probably well over assessment criteria. And if you moved that away, you would see that soil surface was not crusted. And if you did see crusting and bare spots, it would certainly be less than 5% of that field. Water stable aggregates is the next diagnostic tool that we're going to look at today. So when you pick up a handful of soil and it breaks apart into little pieces, you're looking at aggregates. So each aggregate is made up of soil particles of different sizes held together by two things, the attraction of the soil particles to each other and the binding of the organic matter between the soil particles. Add some plant roots, put some life in there, bacteria and fungi, you get your fungal hyphae, all of those things growing in there together. Don't forget that between those soil particles we have pore spaces, and you get a beautiful pile of soil like you have here on the right. All of these aggregates all broken apart into their own little pieces, hanging on and binding to each other. And that soil life plays such an important role in building water stable aggregates because organisms like bacteria and fungi, again, we're dealing with their home here, right? This is their soil ecosystem, and so they would like a stable home, water stable home. And so as they're living in these systems, they coat those soil particles with biological glues, with a lot of fungi, mycorrhizal fungi. It's referred to as glomalin, but they aren't the only ones that coat soil particles with biological glues. So again, think about what we want to see here is that idea of those water stable aggregates, those soil particles holding together, and then all of that, those plant roots and fungi and bacteria and all of that life living in and around and between those soil particles. Whereas on the left we have a picture here of, again, a soil that was bare and rained on and crusted, and when we kind of shovel it up we see it kind of flakes up. We don't see a lot of pore spaces. We're not seeing soil particles of different sizes that are held together. It's just kind of a mash of soil at that surface. And so again, this is an example of not having water stable aggregates or of low aggregate stability. Ultimately, you want to manage for water stable aggregates. Again, when a raindrop falls from the sky, we don't want it to have to roll along or slide along the soil surface until it finds an earthworm channel or a crack. And we're going to talk about earthworm channels later on in the presentation. But those are places where water can go in. But ultimately, we want a raindrop to be able to soak into the soil where it lands. If we have water stable aggregates, an essential part of that, or a key part of that aggregate, is pore spaces, right? And so we want to be able to have infiltration in a well aggregated soil. That water wants to just go right down through around and between those water stable aggregates. That's how we want to manage our soil ecosystem, in comparison to a soil with low aggregate stability, where that soil surface seals and crusts after our aggregates break down, and then we have runoff and we no longer have infiltration.
The test we're going to show you now is a slump test. We've been talking a little bit about different soil covers in residue breakdown. And we have some soil that's clearly crusted over, that's been bare, right? That has had no soil cover. We're going to take a look at how the aggregates act in water in this crust.
This soil here comes from a field that has good soil cover and has been well covered throughout the growing season. So we're seeing that there is no crust at the surface. And so we're going to take the soil from the top inch or so of both of these soils and do the slump assessment on them.
You want to take your screen and your soil from the top couple inches and just start loosely crumbling it into your sieve.
The goal is to not mash the pieces that you crumble into the sieve. Don't mash them. Just let them break down naturally into the sizes or aggregate sizes that they want to break down into. And if you have a soil like I do that has a lot of, say, residue at the surface, try to get as much of that residue off before you crumble it into the strainer.
You can use soil right from the field. That's what this is we just took this a couple of minutes ago. You want to make sure it's not super wet and muddy. If it's too wet, you need to be careful that you're not mashing it. You want it to be able to crumble into the sieves. You want the soil from that top couple of inches. You can see we have the crust here and the top couple inches from the soil health system over there. Because that's what we're the most concerned about, is that near surface interface of the soil and how well that can function.
So we want to get it about 1/2 to 3/4 full. We don't want to have it be too over full. And again, we don't want it to be packed down into that strainer. We want it to kind of just sit there naturally as it crumbles in. And then we take that strainer and we set it down into the water.
Right away, as that soil wets up, you can see the aggregates begin to break down in this one. So you can see particles falling and you can see that water clouding up.
On this one over here, we have some of those aggregates or chunks that are falling out, but if you notice when they fall, they precipitate down to the bottom of the cup really quickly. So they fall down and they're not hanging in suspension or making the water cloudy. So this is just a kind of like a little mini view of what's happening to that soil as it sits in the water.
The water clouding is an indication that those aggregates are completely breaking down into the individual sand, silt, and clay particles. And it's the silt and the clay particles that are staying in suspension and making that water look cloudy.
So we want these soils to sit in here for about a minute, 30 seconds to a minute. You want that sample to completely wet up and get good and saturated before we take it out. Which I think we are pretty good.
Once they've done that, you want to lift them out and let any free water drain off of them quickly. And then you just want to take a flat surface. It can be a shovel, it can be a plate, it can be the bed of a tailgate. That's a little harder to clean off, but it does work. Any flat surface, and you just want to tip that soil out onto that surface.
So right away, we see that they look quite different from each other. And we also see water running out of both of these samples, but let's look at what looks different about them. This sample over here, a lot of those aggregates have melted. Anything that was considered an aggregate has melted, and it kind of almost has like a smooth texture now because those aggregates are no longer there in that pile, in that slump. Whereas here, we have the aggregates are still visible, so you can still kind of see those small chunks of soil that are in this sample. They've held together in the water. So the video showed us how to actually do the assessment. Now let's take some time to look at the results of the slump and when we dump them out onto the plate just a little bit more. The best thing to do when you're working on these slump assessments is to have a comparison. If you read through the assessment guide, it talks about comparing to a non-disturbed adjacent area, which is a great thing to do. But sometimes when you're in the field, you don't always have access to a non-disturbed adjacent area. So what I like to do is I like to look at my assessment area, and I identify two key spots in that assessment. The first spot is an area that is missing all of the surface criteria that we've identified in the previous assessments. So it's missing surface cover, we're not seeing a lot of residue breakdown. I guess we would say it has a surface crust. So again, an area that we would think would have low aggregate stability. And then for comparison, I identify a site in the field that has high surface cover, we're seeing residue breakdown, and we do not have a surface crust. So an area of the field that we would think would have high aggregate stability. And I put those in the strainers to compare to each other. So that's what I have here on this on the top part of this slide. The plate on the left, or the slump on the left, is a sample that has that is a bare soil, a crusted soil. The soil on the right is a soil that was covered, that wasn't crusted. Put them in the water, had them in there for a minute, took them out. Now let's take a closer look at those slumps, up close and personal. So you'll see that slump on the left. Again, that's the site that we would assume, or that we estimate has low aggregate stability. And that slump is showing us that, right? So those aggregates, or those particles, or whatever we had that we put in there, they've pretty much melted away. And the surface of that slump is really smooth. It's all melted and kind of congealed together. And we see that that slump is really shiny. So that indicates that that water is coming out of that soil, and it's on the surface of that slump. And again, really shiny, and then we're seeing that water come out of it on the side. So let's take a look at that slump on the right-hand side. And this slump, again, came from a part of the field where it had surface cover and we didn't see a crust. And so let's take a look at this right here. And what I want to tell you is that it seems like this probably isn't very much better than the slump on the left, right? We see a few aggregates, like we have an aggregate right here, right? But a lot of those aggregates have melted, right? So we see how smooth and shiny it is on this bottom side here, very similar to the slump on the left. And the biggest thing that I want to point out is those areas between the aggregates right here. Do we see how much water is kind of pooling up between those aggregates and over in here again? So that water isn't being held in those pore spaces, and by that organic matter within those aggregates, that water is kind of oozing out and pooling up around between those aggregates. So if I were to look at this, what I would say is that this slump here on the right, it does not meet aggregate stability. And that would actually make sense, because the field that I did these samples in is a field that last fall was its first cover crop was seeded onto it, and it wasn't worked this spring, but that's its first year of a no-till cropping system, and it's had its first season of cover crops out there. So again, we are dealing with a field that's in transition, and so we don't have water-stable aggregates yet. Here's another example of that. You know, again, the samples, the one on the left, you can see there's a little bit crusted there, whereas the one on the right, we don't have a lot of crusting at that surface. And so, again, I go through this process and I dump them out. So let's take a little bit of a closer look at this sample right here. So we're going to go and look at this one first. All right, so what are we seeing here? We can see those aggregates are a little bit more well formed, right? We're seeing where they're holding their shape, a little bit shiny throughout there, but mainly the surface of that slump is the water is soaking in, the water isn't coming out of it, and when we look between those aggregates in those pore spaces, we aren't seeing water pooling in there. We are seeing water coming out a little bit in the bottom, so that's something to take note of, but note how much it is. The thing I like to do with this plate is I like to tip it up into an almost vertical position. I like to see how long it is before that slump actually starts to slide across that plate. The next thing that I do is I take that plate and I kind of tip it in all angles and see how does that slump hold together as I slide it across the plate. And as you can see here, we're seeing a little bit of water come out, right? But we're not seeing a lot of soil come out, a few particles, but not a ton. And that slump is holding together relatively well. And when we look up close and personal at this one, again, we're not seeing a lot of water in those pore spaces, so that water is holding into those aggregates. We're seeing a little bit of water right through here, right? So that there's some degradation that has occurred to those aggregates there. But all in all, we're seeing really good shape being held into these aggregates. So I would call this a water-stable aggregate. So let's look at the other one from that original picture where we had the two together. So we're going to tip this plate up, and we notice right away that that slump slides right to the bottom of that plate. And you don't have to get it very close to vertical before it starts to slide. And then as we slide it around, or we tilt that plate around and we slide that slump all over the place, we have evidence here of that soil being left behind. Again, those aggregates aren't holding together, the soil particles are bleeding away from each other, and we're left with that slump is just kind of spreading out all over that whole entire plate. And again, when we look at that aggregate up close and we look at those slumps up close, we see that they've melted, that sheen on the surface of them in these areas, and that there is really no pore spaces between these aggregates, right? Because the smaller aggregates have melted, and so we have sediment, we have silt, we have clays, we have those waters that are just kind of oozing in between those areas, and so we don't see distinct aggregates in here. So this is an example of a not water-stable aggregate. So here's an example, again, in the assessment guide it talks about going to a comparison site, a non-disturbed area adjacent to the field. So when I was out in the field the other day, I went and I took a sample from a wooded area adjacent to a field and put that in the slump and ran that through the riggers. And this is just a great example to remind you of what a truly, completely water-stable aggregate looks like and what that slump looks like. So let's go through and describe this just a little bit. We see all of our aggregates here, right? So as I tip this plate up, it really holds in place well. You almost have to tip it up to vertical before it actually will move across the plate. And we see all of these aggregates, larger aggregates, smaller aggregates, even smaller aggregates in there. They're all holding together and holding their individual shape. We can see some evidence of maybe some root material through there as well, but when we look in between those aggregates, we don't see water oozing out, right? That water has soaked into those aggregates. The organic matter in there is really holding all of that water in there. And even as we look to the bottom of this slump, we don't see water oozing out or pouring out. It's just held in that slump really well. And then the other thing is as you tip that plate kind of from side to side and see how that slump moves, what happens with this slump is that it actually tends to kind of crumble and open up because those individual aggregates are holding together so well, and they just kind of spread out, and you don't lose your slump, but the aggregates stay formed, and they just kind of open up and are ready to infiltrate more water. So this is an example of what a real water-stable aggregate looks like, and by real, like a really good example of what water-stable aggregates look like. So one last picture of water-stable aggregates. If you can tell, I really like to do this assessment, and I do think it's probably one of the most important ones that we look at through this process. Because it tells us so many things about infiltration, about crusting, about whether there's soil cover there and how our residue is breaking down, and it's really key for a lot of our soil functions. So this one, I didn't mean to do this, but these photos were taken in black and white, and what it shows me is that sometimes if you can take a black and white photo, you stop focusing on the color of the soils and what you're seeing, and more on that contrast between the soils and the pore spaces. And so if you really have a hard site that you're looking at, a black and white photo can help out a lot. So if we zoom into those aggregates, let's take a look at these here. This one here on the left, We have some well-shaped aggregates. We're even still seeing some micro aggregates in there, right? And we are having in those pore spaces, we don't have water pooling up in those areas. We have a little bit of water coming out down here at the bottom, but it's not a ton. And again, those aggregates are actually kind of staying whole and moving out from there as well. On the right, we're seeing a lot smaller aggregates here. They're still holding their shape, although they're a little bit degraded. But if we look around to the sides over here, we're still seeing aggregates throughout this whole entire slump. We are seeing water come out, but again, it's not really very dirty. A little bit of water coming out there. Just observe that and see how much it is and what it looks like. So, although this one has a lot of smaller aggregates, we're not seeing a lot of water pooling up in there. I would say that both of these slumps I would look at and say this is a site with water stable aggregates. And again, when we did the demonstration or when we did this assessment, it would make sense as to where we are. We're out on a site here where we're in a 3-crop rotation. We have a cover crop of red clover here that was seeded and after wheat harvest, and is growing really well. So we had good ground cover, good soil cover, decent residue breakdown. We still saw some wheat stubble in there, but we didn't see a lot of other residues from the previous crops in the rotation. And so we're seeing a well aggregated soil in this scenario. When we look at assessment criteria here, what we want to talk about is that the tool listed, or the guide listed 3 methods for evaluation. We mainly want to focus on the strainer method, or what I like to call the slump method. Again, that's the one that's the easiest to use out in the field. The materials, you don't need very many materials, a little bit of water, a strainer, something to dump that slump on, and it's pretty straightforward. The soil quality test kit, Slake Box, is more of a rangeland assessment tool, so I didn't really talk about that today. And then lastly, the cylinder method, which is also our slake demonstration, is something that you can use to evaluate for water stable aggregates. But with the cylinder method, it is absolutely essential that those golf ball size aggregates you're evaluating are air dry. So you can't do it in the field like you can with the slump assessment. So what we want to think about for meeting assessment criteria is that for the strainer test, we want to have it stand up. We want to see the runoff water be translucent, and think about the things that I talked about. We don't want to see water pooling between the aggregates. We want to see those aggregates holding their shape and not melting away. Those are the things that we want to see when we talk about meeting assessment criteria. Next is ponding and infiltration. This is a very straightforward visual assessment when we want to look for ponding. Again, whether ponding is there or an evidence of ponding is there is what we're looking for. But if you want to go into more depth and kind of look at infiltration, we do have the infiltration rings that were delivered to all of the field offices, and so those are there if you would like to use them. For the basic purposes of the assessment, I don't recommend it. But if you have a farmer who is really interested in understanding soil health and seeing what's going on his or her farm, these infiltration rings are a great way to talk to the farmer about soil health and infiltration and soil function out in the field. And it's a visual assessment that really gets that farmer interested in what's going on out there. So if it is something that you do, I recommend when you pick out your sites to do your assessments that you go out to that site and the first thing you do is pound this ring in the field and pour the water on it. 1 inch of water on these rings is 440 mils. So in the containers that you guys received, there was a white little cup in there, a white measuring cup with a lid on it. And so if you fill that cup up to the bottom lip or the lip of the container, that is 444 mils of water, 1 inch of water in the 6-inch ring. Assessment criteria for ponding or infiltration is to have no evidence of ponding on non-hydric soils within 24 hours following a rainfall event. And if you are looking at infiltration, the best thing you can do is either compare a cropland area to a fence row sample of the same soil type and see if they have the same or different infiltration, or 2, if you just are looking at that assessment within a field, see if that water infiltrates within 30 minutes or less. Now, if we are on a bone dry field in July, that first inch of water doesn't count because then all you're doing is wetting that soil up. And this infiltration method is looking at infiltration of water when the soil is at field capacity. So again, if we are too dry, you need to put water through that ring first, that first inch through, and then you time and measure the second inch. Penetration resistance is the measurement of soil compaction in our agricultural fields. This compaction can result from repeated wheel traffic or repeated tillage at the same depth. Compaction inhibits water and air movement through the soil, in addition to interfering with root growth and soil organism habitat or movement and proliferation through the soil profile.
If you'll forgive the pun, when you're assessing soil function, sometimes you just need to dig a little deeper. And I'm sorry. So a shovel pit can be a great way to gain some insight into what is happening in the soil. You're looking for a hole that's roughly 18 inches or about 2 feet square in order to give you enough room to work. You can see Stephanie taking care not to smash that back face of the soil profile there. And here in just a minute, you'll see her cut one side before she pries that soil up to have a look at it. Of course, you're more than welcome to go ahead and stick your head in that hole and have a look that way, but I really find pulling up a shovelful and looking at it from the surface is a lot easier for me. If you can get a full pit dug, that's great, but that's not always practical, right? So you can gain a lot by just digging a quick shovel pit. Once you have that shovel full, you want to take your pocket knife and just pick away any smearing that you may have caused while you were digging. And you want to be looking for evidence that there might be a problem in that soil profile, right? So you're looking for platy structures, you're looking for horizontal fractures, you're looking for issues with rooting, whether that's a lot of horizontal roots, thickened roots, J roots, that sort of thing. And you can see here that we've got some platy structures. We've got some cracks that have formed there, that have broken apart. And what you really want to do is be able to pull that soil apart and have a look at the faces of those horizontal fractures, right? Because while there may be compaction, what we're really looking for here is limiting layers, right? So we want to make sure that we don't have root limiting layers here. And as you open that face up and have a look down at it, in this instance, you can see all of those holes there, right? Those are from earthworms, those are from other soil critters, those are from roots that have grown in there and decayed away. There's a lot of things that can cause those channels and those pores, and we'll talk about pores and connected pores in a little bit. But while you're digging, you want to be able to just pull this soil up and have a look at it, right? Because we talk a lot about assessing soil function at the surface, but it's also important to be able to dig down and take a look at what's happening in the soil, right? So in this case, we do have quite a few horizontal layers, but there's quite a few holes punching through those, so it doesn't seem like maybe we have a limiting layer here.
Like Joe said in that video, we really want to look for those horizontal fracturing layers where we can try to identify root restricting layers. So in these photos here, like the one on the left, you see these horizontal fractures going into this, going pretty straight in that soil profile that we dug up. There's one a little bit higher up as well. Again, so those are the spaces that we're going to look for and try to identify root restricting layers. So again, if we pick that soil up and we open them up, we keep asking that question, do we have a restricting layer here? And in this picture on the left, we notice that we have all of these plant roots poking through from one horizontal plane into the other horizontal plane. And we actually see those roots continuing down more deeply into the soil profile. And then we take that face or that smooth plane and we turn it over and we look at it. And again, we see all sorts of various shapes and sizes of pore spaces, or biopores is what we're going to refer to those as in a little bit. So again, those earthworm channels, maybe old root channels, and they're continuing on from one horizontal plane to the next layer. So the answer to that question is no, we don't have a root restricting layer here. So how about this one? Do we have a root restricting layer here? Again, a different soil that we're looking at, a different profile. You notice there's a very straight horizontal plane right here, and even some really obvious platy structure right below this. Again, these are two indicators that we want to look at as we start to evaluate these systems. As we open up that horizontal plane and we look in there, we see a lot of, again, plant roots growing down from one soil profile into the next soil profile. So typically here I would say no, we don't have a root restricting layer. The one thing I do want to point out is we are starting to see some plant roots kind of mass together and maybe not grow straight down into that soil plane below that. So again, keep an eye out for those types of things, because this could change depending on, the season and the weather conditions. Lastly, we're going to look at this site where using our cover crops is a great diagnostic tool here. So we're looking at this cover crop here, and we're looking at what Joe referred to as a J root. Look at how many times this plant root had to bend to get through the soil profile. 1, 2, 3 right here. So at least 3 obvious bends in this plant root, and this J root that you notice here. And if you look over on the left, again, you'll see this horizontal plane, very obvious platy structure below that. And then when we pick that up and we look at that horizontal face between the two planes, this is what it looks like. So we're seeing that really obvious platy structure right below that. And then we have this plant root that's growing right inside of that horizontal plane. That root is not able to penetrate or punch through that compacted horizon below it. So do we have a root restricting layer here? Absolutely. How about this one? Again, we got a soil profile that I popped out of a hole, cleaned that face off, and I used a drawing tool to mark a couple of places where I saw some horizontal fractures here. And what I want you to notice is here at about 3 inches down and at about 5 inches down, we're seeing these plant roots that are actually coming out towards us. They've had to modify their growth. They're not growing down as much anymore. They're kind of coming out a little bit. So that's again one of those indicators that we look at when we're talking about those restricting layers. But then when we get down to at that 7-inch depth, again, where we're seeing another horizontal fracture, we look below that and there's plant roots all over down below there. Growing in this soil profile. So do we have a root restricting layer here? And the answer to that question is maybe. We likely need more investigation on this site. And places like this, it's really critical what that farmer tells you is the management on this site. In this case here, we had a field crop, and after it was harvested, a cover crop was seeded into this area. And so a cover crop was seeded in August. And maybe was impacted slightly by the dry weather conditions and was working to get through some of those layers. But we had plant roots below that earlier on in the growing season when we had more moisture to get through there. So these are things that you look through out there and help you to make these decisions for root restricting layers. So we come back to that assessment criteria. And I want to point a few things out with assessment criteria. It talks about 2 tools, a penetrometer and looking for ratings of less than 150 psi within the top 6 inches and less than 300 psi in the 6 to 18-inch depth, or slight or no resistance with a wire flag inserted in up to 12 inches. And if you notice, the last 3 or 4 slides that I talked about, I didn't mention those tools at all. And that's because I really want this assessment to focus on what we're seeing and what those plants are telling us out there, because they are such a great indicator of that root restriction, of that penetration resistance and unable to push through those horizons when they're compacted like that. That being said, one of the things that I do like to do is when I dig my hole and I have my soil profile and I've kind of cleaned it off, I've looked at it and I see these horizontal fractures, I do like to use a penetrometer to confirm that in the field, or a flag where as I'm pushing those tools into the ground, I find that place where I'm hitting some resistance and I put my hand against the ground right at where that wire is and I pull it up and I look at that depth and I compare it to the soil profile. I lay that flag of that penetrometer against the soil profile and I match up the soil surface to the spot where I had put my hand on the penetrometer for the soil profile, and I look to see where that compaction was measured on the flag or the penetrometer. Is that the same depth where I'm seeing that horizontal layer? And if that tends to be the case after 10, 15, 20 measurements around that assessment site, it does help me really to really confirm that that horizontal fracture is probably an issue, even if there's an absence of roots out there in other situations like that. So again, dig a hole. That's the first thing I like to do, is dig a hole. I like to look for those horizontal layers. I like to look for those plant roots and if they're modifying their growth as a result of compaction. And then lastly, I like to support that with a penetrometer or a flag and using that information to kind of support what I'm finding when I dig that hole. Next, we're going to look at soil structure. So our soil structure is the arrangement of particles within the soil. And the biggest thing that we want to look at again is it a granular structure or is it platy? So again, the photo on our left here, we're looking at an excellent granular structure. We're seeing that those aggregates, like we had talked about, if you scoop it up and the soil kind of breaks into its own nice little individual particles and shapes and sizes, those aggregates, we're seeing that all the way to the soil surface here. Whereas the picture on the right hand side, we're looking at that platy structure, those layers of soil particles, almost like sheets of paper stacked on top of each other.
Another important indicator that we have for soil health, of course, is soil structure. And in our Infield soil health assessment tool, we talk about the different types of structure that are both positive and causing possible limitations. So the thing we want to look for positive, on the positive side, is granular structure. We should have granular structure, meaning you should be able to see the soil aggregates right at the very surface. So we have to have a shovel, and so we go digging into a field here that has had some tillage history in the past, but as we dig down, we're immediately seeing platy structure, but in the very surface, if this were granular structure, we would be able to see the aggregates. It would break apart in a nice granular crumb. And what we're seeing is this soil is still staying pretty blocky. The structure is not really granular at all. It's even bordering on a massive type of or a structureless surface layer. There are a few organisms that are starting to work this, because it is in a minimum tillage situation. However, the kind of structure that we're looking for as far as granular structure just isn't present here. So all it takes is, that we immediately see platy structure. We don't see our granular structure, so we probably are not meeting the criteria for that indicator.
So to finish up on the assessment criteria for structure, we want to look for that granular structure, the soil surface. We don't want to see any platy or massive structure in that top foot of soil. So if we look at these pictures here, this one on the upper left is a great example of a good granular structure. We see all of those aggregates forming around those plant roots, and we see that nice aggregate structure at the surface of the soil. Again, here on the top right, We have two examples of what would be considered a platy structure. That top picture is a platy structure that was at that 4-inch or 5-inch depth range, and here we got an example of some platy structure right at that soil surface. Again, so we're seeing that that platy structure in those systems, and so that's not meeting criteria. And then lastly, with that picture on the lower left, we have a field here where we've recently added cover crops into this system. So we're starting to see that granular structure really come back into this system. But we are still seeing that platy structure at the surface. And so this again would be an example where we're working into this system, but it's not meeting the assessment criteria yet. The next assessment we're going to look at is soil color. And soil color is related to organic matter content, and really with this assessment, the focus is wanting to look at these trends over time. When we look at soil color, darker soil colors would indicate, higher organic matter or systems where we're building organic matter, whereas lighter soil colors would indicate that we have a lower organic matter or systems where we're depleting that organic matter. And so those are just some of the things that we want to think about here, that color is an indicator of loss or accumulation of organic matter. Two of the ways that you can assess this is to dig a hole in the field, and then if you know what that soil type is, or you have that web soil app on your phone so you can look at that pet-on description from the official soil survey, you can look at what the official soils or the official series description color is for that soil surface, and you can compare that to what you're actually seeing out in the field. So that would use you'd need to have your Munsell soil color book with you, and make sure that you could compare that color and see if it fits within the range of what's identified for that soil type. Or you could dig a hole, look at that soil surface or look at that color at the soil surface and compare it to an adjacent non-cropped area, an undisturbed area where we would likely see higher organic matter in that undisturbed area. So the reason why we really want to think about organic matter changes over time is that, here we got this kind of hypothetical graph that I've made up, and we see here we have a 2% increase in organic matter over time, over 20 years. And if you do the math on that, that's 0.1% of increase of soil organic matter every year. And that, although that may not seem like a lot when we think about, percentages and actual numbers, 0.1%, from the terms of organic matter accumulation, that is a significant amount, and really that's kind of the changes that some of our advanced soil health systems are seeing, where farmers are intentionally using high biomass cover crops and taking out a lot of disturbance. Those farmers will actually see 0.1% of an increase over time. But the reason why I speak to that is that percentage organic matter change is really a difficult thing to measure, and it doesn't really show up from year to year, and it takes a long-term program to see these changes over time. And so and sometimes that's really hard to work on with a farmer when you're saying, well, you're going to build organic matter over time. So these are nice ways to look at that soil color, and instead of you want to focus on the positives of building, but sometimes that's also helpful to show that you don't want to have depletion. And if our colors are lighter, or like here in this picture where we have the undisturbed soil clod adjacent to the worked field here, we are seeing a color difference. We know we have a loss of organic matter, and this is in a field that's in a high organic matter prairie soil, and we're seeing less organic matter. So this loss happens to every soil and every system type. So again, our assessment criteria is to look for if we have an obvious darker surface layer, and it is similar to the series description, then we would meet criteria. Again, and if we compare it to an undisturbed adjacent area and they're the same color, then again that indicates that we are meeting assessment criteria. Next, we're going to look at plant roots for assessment. So the last three assessments that we're looking at here all have to do with living things, living organisms, or the remnants of living organisms. So plant roots are so awesome to look at and evaluate for this assessment because they exude simple and complex carbohydrates that influence our soil microbes and also influence soil structure by helping to form soil aggregates. So they have this zone of influences immediately adjacent to them, and so ultimately what we would like to see out there is maximizing a plant root's zone of influence by having as many roots in the soil for as long as possible, right? So some of the things that we want to look for when we look at plant roots is we want to see that healthy structure, that plant root is growing down, nice straight down into the soil. We want to see those aggregates that I just talked about forming around those plant roots. So this soybean plant here in the middle, we got these aggregates that are hanging on those branch roots there. Even on this little tiny radish seedling or whatever brassica seedling this is, we got these tiny little root hairs there, and we have all of these aggregates forming around those plant roots. And then lastly, we want to see, like in this upper left-hand corner, that rhizosphere, that rhizosheath around that plant root. And we're going to talk a little bit more about that in the next slide. So again, we want to look at these plant roots and we want to see what they're telling us about the system that's there. So we just are going to go through some of these pictures and talk about each one of them. So this plant in the upper this root in the upper left-hand corner, in this black and white picture, you can see I dug this clod out. It's after harvest. So again, if we look at that assessment criteria, it wants us to evaluate during the growing season. But this is when I was able to get out there, and if you can assess plant roots, you know, these are the things that you want to look at for remnants. But this plant root hit a compaction layer and we have sideways or lateral growth. So again, this is a restricted or you know, an example of a plant root not meeting that criteria. Now this is just one plant root here, and in this situation I'd probably dig up, you know, 5 different more sites, just poke a shovel in the ground and dig up that surface soil layer in those top 4 to 5 inches wherever I found that layer, and look to see if I'm seeing that consistently, because that again would tell me that that's a predominant issue affecting plant roots in that field. Here we have this picture in the middle where we're looking between 2 horizontal planes, and if you notice we have all of these plant roots, they're kind of massing on those planes right there. They're not growing between them. So when you open that soil, that horizontal plane up, that layer, we open them up, we see those plant roots growing along the walls of those horizontal planes. And so again, those plant roots are balled up, growing along the horizontal plane. This is an example of not meeting assessment criteria. Here on the upper right, we're looking at a young corn seedling, and we are looking at that young seedling root growing down. It's so nice and straight, and the thing that we want to point out here is the rhizosheath. Again, so that plant is actively, or that root is actively exuding carbon even at that age, and what its goal there is to activate that soil biology with those simple carbohydrates. Get everybody excited with a bowl of Fruity Pebbles at 6 o'clock in the morning, and get everyone all hyped up and working for you. And so that rhizosheath of that coating of those soil particles along that plant root is an evidence that that plant is actively exuding carbon into the soil and actively recruiting soil organisms to right around that immediate plant root to start working for it and help build function. And that's an indicator, that rhizosheath is an indicator that that plant is actively influencing the soil to help build aggregates around it. All right, so then on the next row here, we're looking at this winter annual weed that's growing, and what I want to point out here is we see a lot of plant roots, right? But what we don't see here is we don't see a rhizosheath on those plant roots. And so I guess the thing that you want to think about when you're evaluating plant roots is that a lot of our broadleaf weeds don't exude a lot of carbon. They don't create a rhizosheath. They don't, those things aren't happening, and so their influence on building aggregates and activating soil biology is really minimal. And so as you're doing an assessment in a field, if you decide to dig up some winter annual weeds like this after harvest and say, well, I see some plant roots, and so we meet assessment criteria, the thing you want to ask about is do we have rhizosheaths? Do we have aggregates forming on those plant roots? And we really don't here. And so if this is the predominant system out there that is just those weeds and nothing else is growing, we may have roots, but we're not really doing a lot for building that system. And then lastly, we want to look at this balansa clover root that we have growing here. Notice that branching that we're seeing. Again, it talks about being branched, healthy roots, and how that main taproot is going straight down into that soil profile. So this is a great example of a plant that's meeting assessment criteria. So now we're going to look at biopores. Our biopores are plant roots and earthworms leave behind these large pores, and we call them biopores because they're created by living organisms. They're important for rapid air and water exchange. So again, when we think about a massive rainfall coming down, again, our water-stable aggregates and the pores that are around those aggregates are essential. But when they get saturated or they get soaked full of water, these biopores help soak up a lot of water really quickly, or again, as that water infiltrates in the soil through those biopores, those biopores rapidly help pull oxygen back into that system so that they don't become oxygen depleted. So let's see some more examples of biopores. So these biopores, the biggest word that we want to highlight here is continuity. So when we talk about continuity, when we are talking about biopores, we're meaning that we want to see them connected to the surface of the soil. So if we look at this photo here in the upper left-hand corner, we're seeing some biopores, right? Some remnant worm channels kind of coming up into the soil profile. But and this is the soil surface. The top of this clod here is the soil surface. But what we're seeing is we're not seeing continuity to the soil surface, and we're actually seeing a pretty thick crusted layer and that platy structure before we get to those channels. And so this would be an example of a biopore or of biopores not meeting assessment criteria, because again, when I was out on that site, the entire area that I was looking at looked like this. And so again, we're not having that continuity of those pores extending vertically through the soil and coming to the surface. Whereas in comparison on the right-hand side here, we have a great example of some biopores going 36 inches deep into the soil. So we can see that was an old earthworm burrow. And we can tell by the darkened color that biopore is, that earthworm, is pulling soils and organic matters deeper down into the soil profile. And then those castings were pushed out of the worm and line the inside of that biopore. So those earthworm burrows or those channels become nutrient-dense root channels. So we can see, for example, here right next to that, we have this plant root that's growing down an adjacent old earthworm channel right there, taking advantage of the nutrients, the plant available nutrients that are in those castings in that channel, but then also taking advantage of the ease with which that plant root can grow through that biopore and deep into the soil, subsoil very quickly. Case in point, this plant root that we're looking at here, this is a cover crop that was seeded after a wheat harvest, and this soil pit was dug 30 days after the cover crop was seeded. So that plant put on massive root growth very quickly, and again, taking advantage of those biopores. I like to call those the super highways for our plant roots, because they can push their way down very easily through that, and they don't have much resistance in any potential compaction layers or other things like that they would have to deal with in the matrix soil. All right, so here on the lower left-hand side, we're looking at, again, a winter annual weed, and we all know that they don't have the rhizosheaths, but I just want to point out a biopore here in this bottom corner where we had an earthworm channel that went all the way up to the surface and is going down deeper into the soil profile, and how those plant roots kind of mass in that channel and grow through there. It's a great example of a biopore. And lastly, here's an earthworm channel where we're seeing, we're seeing castings from the earthworm. We're seeing some evidence of residue that's been pulled into there. So it indicates to us that there's continuity, that channel went all the way up to the surface. It's darkened. We're actually seeing some a plant root, a very small plant root right here growing in this biopore. So again, great example of a connected, biopore that's connected to the soil surface, and that continuity of these biopores providing the benefit that they provide to our plant roots, and again for air and water exchange. So lastly, we want to look at biological diversity. We want to look at this based on the ratings of observations of the presence of organisms within that area that we're evaluating. And this is such an awesome one to look at, because there's as we build our soil health systems, we see the diversity of our organisms increase significantly on these sites as we improve the space in which they can reside, but then also improve the habitat for the above ground organisms as well.
One of the other indicators that we're looking for, of course, is biological diversity. And as we look at a particular sample area, we're looking for, maybe we're here in the middle of the winter. It's not a time when organisms are very active. So it's maybe hard to find some of those organisms that you would find in the spring or the summer or even the fall. However, we still can look for, are the biological hotspots, are those areas of habitat that are important to biology present in this? And from doing that, you can kind of pull back some of the residue that was recently deposited and get some idea what kind of habitat did we have, the surface mulch, the surface cover, the detritosphere. Did we have that really important biological hotspot present through the summer? And the answer in this particular case is probably not, because as we scrape back the fresh residue and look underneath, we're seeing that it was pretty bare soil most of the summer. And so the evidence is pretty clear then that at least a really important biological hotspot is missing. Biological habitat is missing in this particular management system. So that's one way that you can kind of, if it's a bad time of year for really finding organisms, then you have to look for evidence of organisms. If you can't find evidence of organisms, then you can look for those really key habitat zones that the organisms are going to need.
So in that last video with Barry, it got a little bit windy, so it was hard to hear him towards the end. But really the key things that that he really talked about there is ultimately we want to look for organisms. We want to look for those, be able to count the number of species. But if we're out there at the time of the year when it's not the best time to look for organisms, we want to look for evidence of organisms. And if we can't find evidence of organisms, we want to start looking for those hot spots, those known areas within our soil or above our soil where we know that that we're likely to find soil organisms. So again, like he explained in the video, looking to see if we had good residue cover, right, that soil cover during the growing season, because again that detritus on the surface is important for our spiders and our other macroarthropods that are responsible for shredding residue and breaking it into smaller pieces to facilitate breakdown. So just a little bit on biological activity. I know the purpose of the assessment is to count the number, right? The number of different species or different organisms out there. But if you're out there with a farmer, one of the things that they love to look at it is earthworms, and talking about earthworms, and knowing that they have these creatures doing that tillage work for them in the field and pulling those residues down into the soil. So one of the things that I like to do is really talk to them about the presence of earthworms. And here in this picture we're talking about night crawlers. And so if you can look in here about approximately a square foot of soil, we might be a little bit larger than a square foot, but let's just approximate here. And we have about 23 nightcrawler middens right here in this square foot. And if you can, I teach, kind of show farmers how to identify those in their field. That's really an exciting thing for them, knowing that that worm again is pulling those residues and putting it over their burrow to create like a little mushroom cap there to protect it from a lot of the rapid infiltration of the water, but then also that those residues are composting there, and so then as those residues start to break down and decompose, worms pull those down into the soil profile, basically putting organic matter deep into the soil profile that becomes long-term organic matter. But then also as those residues are decomposing, there's bacteria and fungi in those residues, and worms really like to pull those in and eat those, and then as they're moving through that profile, they're redistributing that bacteria and fungi in the soil profile for them to increase that bacteria and fungi numbers and have them do work in different areas in the soil profile. So one of the other things I want you to think about here, as I said, there was 23 middens, and so let's talk about this number that pops into my head, which is 1,001,000. And you're like, so what does that number mean, Stephanie? And what does 1,001,000 mean? So basically, if you take these 23 nightcrawler middens and you multiply that times 43,560, which is the number of square feet in an acre, you come up with a number 1,001,000, or approximately 1,001,000, plus give or take a couple hundred other earthworms. And so that's the number of nightcrawler middens that you could potentially see in an entire acre of field, or entire acre of this field. And think about the impact of that. The way that this, we look at these small sites and people get excited about this, or, we look at these small areas for evaluation. And when you really want to get farmers excited about this, extrapolate this out to like an acre or an entire field, and think about the life that is thriving within that system as they're working so hard to build it. And again, these populations support numerous ecosystem functions. Earthworms are great for improving or involved in aggregation and soil organic matter formation, and help nutrient cycling and disease suppression and detoxification of the soil. So again, lastly, when we talk about biological diversity for assessment criteria, we just want to talk about the types of organisms observed. And it talks about more than 3 types of organisms observed. We want them to be clearly evident, so you don't need to have a microscope out there to see them. You need to see them with the naked eye, and they need to be 3 types of organisms. So let's just talk about earthworms again. So if you have a red wiggler worm and a nightcrawler, a worm is a worm is a worm is a worm, right? So we have worms. Worms only get counted once. No matter how many worms you see out there, no matter how many different types of worms you see out there, a worm is a worm is a worm is a worm. But let's think about some of the other things that we can evaluate and count towards meeting this criteria. So on the lower left here, we have some examples of some saprophytic fungi. You guys will see this in fields a lot, where we're seeing those white masses of either those hyphal threads, or again white masses growing in the fields, and that's examples of our saprophytic fungi. That would be evidence of an organism. Again, because it's kind of hard to see a fungi itself, but those hyphal threads are evidence of that organism. Here a picture in the middle with, again, that legume root with those nodules on there. If you can see active nodules on a plant, you can count that as evidence of a organism. Again, because that nodule in that symbiotic relationship, that rhizobium bacteria is residing in that nodule and actively fixing nitrogen from the atmosphere and giving that nitrogen, plant available nitrogen, to that soybean plant. So that's a great example of another evidence of an organism. And then lastly, I guess I want to talk a little bit about pests. If we see pests out there, do we count those for assessment criteria? Yeah, because they are, different organisms and different types of organisms. That being said, if the only things that you can come up with when you're counting organisms are pest species, two things. One, you want to talk to your farmer about that and, make them aware that as you look at biological diversity, you're only seeing pests out there. And then two, that's really a great time to have a discussion with the farmer, and even for us as conservation planners to think about how this is an example of a system being out of balance when the only thing that's out there are the pests that are causing damage to our systems. So lastly, we want to go back and we want to take a look at this infield soil health assessment decision tree. And I took a little bit of time to put some little handy dandy icons next to the assessments here. The first icon I want to point out is this little heart with the blue outline. And you'll notice that I marked 3 assessments: water stable aggregates, soil structure, and plant roots. And the reason why I marked those is because those are assessments that are applicable to all 4 of our soil health resource concerns. The next thing I marked out here is some little stars, and those are indicate or mark out the assessments that are applicable to 3 of the 4 soil health resource concerns. So again, the stars are looking at soil cover, biological diversity, and biopores. The reason why I wanted to point that out is because as a planner, if you're needing to go out in the field and do these assessments, you want to try to maximize your bang for your buck. You want to get as many assessments done out there that you can, but you also want those assessments to be applicable to as many of these resource concerns as possible. So again, you're maximizing your time out there. You're creating some efficiency by critically selecting these assessments that are applying to more than one resource concern. That being said, the other thing that I want to point out here, just in having done this 50, 60, 70 times in the last couple of months, is that when you go out to a site and you pick out where you're going to do your assessments, and you set that bucket down and you start working, those first 4 surface assessments of soil cover, residue breakdown, surface crust, and water stable aggregates, you can bang those out really quickly because they kind of naturally feed into each other, and you can kind of get the results and work on them as you're evaluating that site. Again, if you have soil cover or not, and then is it breaking down? If you don't have soil cover, do you see a surface crust? And then if you have, as you pull that back and you look at that surface, digging some soil up and quick checking for water stable aggregates. Those 4 assessments can be done really quickly, and they kind of help you get a good feel for the site. And if you look at the assessments there for at least 2 or for at least 3 of the assessments, the soil organism habitat loss and degradation, organic matter depletion, and aggregate instability, those first 4 assessments actually can feed into 2 responses. And if you notice, soil organism habitat loss or degradation and aggregate instability, ask if 2 or more indicators are not meeting assessment criteria. So you can get a lot of work done and quite a bit of evaluation completed by just spending some quality time on those surface indicators. And then if you need to, dig that hole, look for those horizontal fractures, look for those penetration resistance and plant roots and structure, and that can really feed into the rest of the assessments that you need to do to get the rest of your information. Lastly, I just want to point out that yes, there is an app for that out there. The Cropland Infield Soil Health Assessment app was developed about 1.5 years ago. And it was feeding into or based on the old assessments, and it now currently needs an update to match with the new tech note, and I think that that'll be going on hopefully in the near future. And once that gets released, I would like to be able to share that with all of you, because I think that will hopefully streamline the assessment process and the amount of things that you have to, the amount of paper and pencils that you need to take with you out into the field. Because right now a lot of people use their phone to take their pictures, so if they can put their site ID and the findings that they have out there on their phone, then that can really limit the amount of other things they have to take besides the assessment tools. And then lastly, a brief discussion on grouping fields to form management units. So this is a discussion really to think about the fact that when we go to do these assessments, how many of these do we have to do out there? And is there a way for us to combine fields to look at management units on a larger scale? And the answer to that is yes. We want to look at management units based on having the same cropping system and the same management applied on them. And then we want to also group them based on soils. So in this example here, if we created our PLU and CD and exported that layer file into Web Soil Survey and clipped out our soils map and generated our brief soils description and all of those other wonderful things that we need to do. And then we find out that we have two fields where the predominant soil is a Crosby A Crosby silty loam. Then we should be able to combine those fields and do the assessments on that predominant soil type in this situation. So thank you for your time today. I hope you enjoyed going over the soil health assessments, and if you are working on these in the field, please give me a call. I'm more than willing to assist with assessment collection and inventorying process as people are working on getting this figured out. And if anyone needs any more training, please route that up through your RMS, and I will be more than happy to help you. Thanks again.